Hi everybody, this is your lecture 10, part 1. In this lecture, we're going to see how to perform chi-squared goodness of fit test. So let's go back to week 1. In week 1, we have seen that there are two types of data. Do you remember that? Yes, qualitative and quantitative data. Last week, we have seen how to test a quantitative data using t-test. Now, how do we test a qualitative data? That is when data is qualitative, categorical. We can't use the t-test approach. We need an alternative approach. So let me take an example for you to see what type of data are we talking. What is this qualitative data and how to test it, yeah? So for example, if a scientist is performing a genetic cross in which the scientist knows the genotypes of the parents, then based on the genetic theory, the scientist might claim that the cross will result in a certain ratio. But then, how can the scientist prove that her experimental data and the theory agree to each other? How does the model fit? How does the scientist answer to such questions? That is, what if the observed, that is the experimental data, do not actually match with the theoretical calculation, that is the expected results? How can the scientist be sure if this deviation is not a chance event? So these questions can be answered using a chi-squared test. So there are two types of chi-squared test. One for goodness of fit test, and the second one is chi-squared test for association or dependency. So we're going to see this in part 1 and this in part 2. Okay, so let's start with an example to understand how to perform a chi-square test for goodness of fit. Yeah? So consider the situation where a scientist believes that the seedlings from a cross between red and white flowering plants, that is red and white flowering plants, should result in a 1:2:1 ratio in flower color. That is 1:2:1 ratio. Yeah. So you have, if you cross between one white and one red colored flower, you get one red flower, one white flower, and two pink flower. So that's the expected result, theoretical model. That is based on the scientist's genetic theory. Okay. So now the scientist performs the experiment. Yeah. Let's take the scientist as a lady scientist. Yeah. In general, I'll just say, it's a lady, okay? So the scientist performs an experiment and observes the following frequencies. What does the scientist observe in her experiment? She sees that there are 52 red flowers, 168 pink flowers, 66 white flowers. There are 3 categories here. One is red, second is pink, and third is white, okay? Okay, so let's add 52 plus 168 plus 66, which gives you 286. There are total 286 flowers. Of that, 52 are red, 168 is pink, 66 is white. This is her experimental result. This is what she observes. So that's her observed frequency. So I will represent it as O, observed frequency, okay? Now, her theory says that she should expect 1:2:1 ratio of these colored flowers. How is she going to test whether her theory, her model, and her experimental data agree with each other? How does the model fit the experimental data? How is she going to see that? How can she test her theory is correct? So for that, she has to calculate the expected frequency using the ratio 1:2:1. What is the expected ratio, expected frequency of these flowers? If the theory is correct, we can find what the theory would predict for each color. Yeah. So We know the total observation is 286. Now following a theory, we can divide them into 1:2:1 ratio. So 1 plus 2 plus 1 plus 1 plus 2 plus 1 is 4. So out of 4, one part is red, 2 part is pink, 2 parts of the flower is pink, 1 part of the flower is white. Okay, so let's divide that to find the expected frequency. So 1 part is 1 out of 4 parts is of the total is red colored flower. Similarly, 2 out of the 4 parts of the total is pink colored flowers, and similarly for the white colored flowers. So we can now write down the expected frequency for each of them. We can write down the expected frequencies for each of them, each of the flower, following this 1:2:1 ratio. That is following the model, following the theory, genetic theory. Yeah. Okay. So these are the expected frequencies if her theory is correct, if the model is correct. Okay. Let me erase all of it. Okay. So now we can see that the total is again 286 because it has to be 286 because we have applied a theory based on this total value, isn't it? Okay. The observed frequencies don't agree exactly with the expected frequency. You can see that 52, 71.5, 168, 143. It's not exact value what her theory has given us, isn't it? So, but we would be surprised if the theory and the experimental data would have matched. Again, are they close enough to say that the theory is correct? Can you say that the theory is correct based on this? And are the differences too large for the theory to apply? So such questions can be only answered if we perform a hypothesis testing. The more different the observed and the expected frequencies are, the less likely the model applies. Or here, in this case, the genetic theory applies. Testing whether the observed data fits a specific model is known as goodness of fit test. So that's what we're going to do now. Okay, when we have qualitative data and we wish to perform a goodness of fit test, we use a test called chi-squared test. The chi-squared or chi-square statistics is calculated using this formula. That is, chi-square is equal to sum of this whole expression. And what is that? This is observed frequency, that is from your experiment, and this is from your theory, expected frequency. So difference between the observed frequency and the experiment frequency squared divided by the expected frequency. And the sum of all of it, sigma, that is, will give you the chi-square statistics. Okay. So O is the observed frequency for each category. So how many pink flowers are there? How many red flowers? How many white flowers? And E is the expected frequency for each category according to the theory of model. Okay. One more important thing. This measures how different the observed values are from what would have been expected if the theory were true. The greater the difference between the observed and the corresponding expected frequency is, the larger the chi-square value, isn't it? If the difference is large, for example, if O is equal to E, the observed frequency is equal to expected frequency, chi-square will become 0, which is not going to happen in real life. Yeah, that will not happen in real life. But as they get closer and closer, the difference is getting smaller and smaller, and chi-square will become smaller and smaller. Similarly, as the variation increases, the greater the variation, the difference is large, and chi-square value is large. Okay, since we are performing a test, we need to state a hypothesis for the test, isn't it? Whenever we have a hypothesis to be tested, we have to state the hypothesis, just like last week. So again, H0, the null hypothesis should be no change. That is, the model explains the data, data fits the model. And the alternative hypothesis is the model does not explain the data. This is what if we expect the observed and expected frequency are close to each other, as I mentioned just now. This is what when we expect the observed and expected frequencies are too different. For the cross between the red and the white flower, for our example, we have already seen, yeah. So far, we have stated the null hypothesis. We have stated the alternative hypothesis. We have calculated the expected frequency. Now the next step is to, so this is your actual value, experimental, and this is from your model theory, yeah? Okay, so now after this, what we have to do is we have to calculate the chi-square statistics. So for each category, we have to find the difference, square it, and divide by the expected frequency. Okay, so for each category, and then you add it up. So let's do for each category, yeah? So for the first category, 52 minus 71.5 whole square divided by the expected frequency, 71.5. Similarly for the other two. So we have done that for 3 categories. That is red, pink, white. And then use your calculator and sum it up. So that is your chi-square statistics. But what does this value mean and how do we test the hypothesis? That's what we're going to see now, okay? Okay, to see that, we use the chi-square table. You have a table, just like we had tables before. Again here, what is that? Good, that's the degrees of freedom. These are the smaller values of chi-square when the observed frequency and the expected frequency are very close to each other. These are large values of chi-square when the observed and expected frequencies are very far away. If in theory, a small value of chi-square means there's a strong correlation between the categorical variables, yeah? I have just mentioned that, yeah, if chi-square is equal to 0, in real life, that's not possible. This is an unlikely event, yeah? I've just mentioned before, yeah? Okay. Now, how do you find the degrees of freedom? Okay. With the goodness of fit test, the degrees of freedom is number of categories minus 1 or the number of pair of frequencies minus 1. Okay. So for our example, we had red, white, and pink flower, 3 categories. So 3 minus 1 is 2. So K for our example is 2. Okay. So now that is 3 minus 1, red, white, pink, minus 1. Yeah. So we look in the table, chi-square table, look for 2, and we just look for where the calculated value of 10.1 with 2 degrees of freedom is significant at 1%. We look where the 10.1 lies. It lies between somewhere here, isn't it? It lies between these 2 values. So that means the calculated value of 10.1 with 2 degrees of freedom is significant at 1% level. Yes, because 10.1 lies between 0.99 and 0.995. In other words, we can also say that there is less than a 1% chance we would observe the frequencies. This is our experimental data. There is less than 1% chance that we would observe the frequencies. We would observe the frequency 52, 168, and 66 if the null hypothesis were true. That is, if the model is applied. Okay, so that means you can reject the null hypothesis. So therefore, the observed frequencies are too different from what the model predicts, and so we reject the model. That is, we reject the null hypothesis. Yeah, good. Now, testing the chi-squared value in a goodness of fit test. So there are two ways to conclude this test. So in the previous one, we said that it is significant at 1% level. So let me just conclude it so that you can easily conclude. Yeah, give a nice, beautiful explanation for it. Yeah. So it is, the test is not significant. That means that is less than the critical value for the degrees of freedom. The observed frequencies are sufficiently close to those predicted by the model. And so you accept the null hypothesis, that is, the model does explain the observed frequency because they are close to each other, significantly close to each other. Then the other case is significant, that is greater than the critical value of the degree of freedom. Yeah. The variation of the observed frequencies from those expected by the model are too large. Yeah, they're very far away. The difference is large. The observed frequencies are therefore unlikely to be due to chance if the model were true. So what do you do then? Yes, you will reject the null hypothesis and accept the alternate hypothesis that the model doesn't explain the observed frequencies. Okay, so when you are given, when you have a qualitative data, how do you perform the goodness of fit test? You first state the null hypothesis, that the model explains the observed frequency, then you state the alternative hypothesis that the model does not explain the observed frequencies, then you determine the expected frequencies using the model, and then you calculate the chi-square statistics, and then you compare the chi-square statistics with the critical value using the table for the given degrees of freedom. And then you beautifully conclude that whether the chi-square is significant or not significant, and accordingly accept or reject the null hypothesis. Okay. This will be, as usual, this will be given in the exam. Yeah. Okay. For small frequencies, what do you do? That's a special case. When we have small expected frequency that is less than 5, we should group them with adjacent cells to form cells with an expected frequencies of 5 or more. I'll show you an example here. For example, consider this following frequencies where the expected frequencies are determined from some theoretical model. It's just an example for you to see, okay? Look at that. Here you can see that the expected frequency 2.1, you see, it's less than 5. So you combine this cell with the adjacent cell, with this cell. So now you can redraw this as I've removed this cell and I've added to this. Let me add that to you. Yeah, 7. 4 plus 3 is 7. 5.8 plus 2.1 becomes 7.9. So now you see how many categories are there here? How many categories are there? 1, 2, 3, 4, 5, 6. There are 6 categories, but how many categories are here? Good. 5 categories, 1 less than the previous one. Why? Because you clubbed these 2 together. Yes. So we calculate chi-square as before, but the degree of freedom is now, that's right, 4. 1 less than the previous one. Good. Okay. When we calculate chi-square, we are usually looking to see if the value is significantly large, okay? However, because you have in the formula observed minus expected frequency whole square by the expected frequency, the sum total of it, a very small value of chi-square means that as I explained before, the difference are extremely close to the predicted frequency because they are very close to each other. The difference is small. So if chi-square is, for example, is 0.45 with 4 degrees of freedom, then it has a probability of less than 0.005. Look at that. It should lie between somewhere here, because chi-square is 0.45. If you look into the chi-square table, it will lie between here. That means it has a less than 0.0005 of probability is less than that, yeah? Less than 0.05. Sometimes a very small value should raise concern that the data is too close to the theory, indicating that the data may not be genuine. In real life, what will we do in such situations? Good. So, summary of testing a goodness of fit. So first, you state the null hypothesis, state the alternative hypothesis, set the level of test, determine the expected frequency, calculate the chi-square statistics. For the given degrees of freedom, use the table and decide whether chi-square is significant or not significant. That's all for now in part 1, guys. See you in part 2.